Hello everyone, I'm Minsoo, a PhD student at the University of Illinois. Today I'm going to present my research work, Adaptive Prestressing System for Concrete Crossties using shape memory alloys, which was done with my advisor, Professor Andrawes. Concrete crossties are typically prestressed with straight, high-strength steel wires along the length of the tie. The main problem with the concrete crossties in structural point of view is the uneven ballast condition. As you can see on the slide, there are two main failure modes due to uneven ballast conditions, center binding and the lack of rail seat support. In center binding case, the center of the tie is only in contact with the ballast, which will cause the tensile cracks at the top under the repeated wheel loads. Similarly, the bottom of the rail seat region is prone to tensile cracks under lack of rail seat support conditions. So the bottom of the rail seat and the top of the center section needs to be pre-stressed to prevent these tensile cracks. In this research, the new pre-stressing system was proposed to locally pre-stress the target regions to overcome the limitations of the conventional pre-stressing system. To best explain the concept of the new pre-stressing system, I'll compare it with the manufacturing process of the conventional pre-stressing system. First, a conventional pre-stressing system needs pre-tensioning of wires. Usually it is done in precast plants with hydraulic jacking. However, new system does not require pre-tensioning process in the plant because the SMA wires are available in pre-tension condition. And next, the concrete is cast. And in the demolding stage, the pre-tensioned wires are released, and this is when the pre-stressing force is transferred to the concrete in conventional system. However, in new system, nothing happens in demolding stage. This is just like demolding of a precast reinforced concrete member. Demolded ties can be stored in a storage or curing, and once the concrete is fully cured, we can activate the SMA wires to apply the pre-stress. By delaying the activation of SMA wires, we can minimize the pre-stress loss from creep and shrinkage of the early age concrete. So conventional system is more like global pre-stressing because a constant pre-stressing is applied throughout the length of the tie. Pre-stressing is applied to the whole tie, even at the unnecessary regions like end regions or compressive zones. Only constant level of pre-stressing is in longitudinal direction is available in the concrete crossties. However, the new system is more like local pre-stressing, which can apply variational pre-stressing. The new system can pre-stress the target region only and can adjust the stress level depending on the demands of the section and able to apply in any directions. And this is all possible with the shape memory alloys. SMA is a group of smart materials which has a unique characteristic called shape memory effect. Shape memory effect is a phenomenon that the material recovers its original shape from deformed configuration by the change of temperature. So let's say we have a SMA wire in the room temperature, and then we pre-strain it to a certain amount, and the wire can recover its original shape when the heat is applied to certain temperature. However, when the wire is fixed when the heat is applied, then the recovery stress is developed within the wire instead. This recovery stress is the source of pre-stressing force in the new system. To prove the concept of local pre-stressing using SMAs, small-scale tie specimens were designed and tested. The target regions are the bottom of the rail seat and the top of the center, and SMA wires are placed at the target regions. To take advantage of the free wire profile along the length of the tie, straight or U-shaped wires were tested. Also, different level of pre-stressing force was applied to the rail seat and the center section, depending on the demand, which was not possible in conventional system. With the test specimens, the activation test was performed. SMA wires are heated using electrical resistivity. I connected the lead wires at the end of the SMAs, and they are sticking out of the concrete and hooked up to the power supply. Digital image correlation and strain gauges captured strain distribution of the specimen during and after the heating. And this is the result. The DIC results show that the compressive strains were concentrated at where the SMA wires are located. And this proved that the pre-stressing force was applied at the target region as designed. However, the concept of local pre-stressing can be further improved to be more suitable for the commercial application because the system doesn't solely rely on SMA, but it works with the use of small fraction of SMAs. So we improved the design of local SMA pre-stressing system to be more economical and practical for commercial application. This is the improved system. We name it Adaptive Pre-stressing System. Instead of using the entire length of SMA, we only need small fraction of SMA, which we call fuse. And we connect this SMA fuse with the conventional high-strength steel with the connection mechanism. And we cover the sleeve on it to unbond the APS with surrounding concrete, only to our target region. So now we can divide APS into 3 zones. Zone 1 is unbonded SMA fuse zone with a connection mechanism. Zone 2 is unbonded steel, and Zone 3 is bonded steel, which provide an anchorage. Zone 1 and 2 is unbonded to concrete, so when the SMA fuse is activated by heat, both Zone 1 and 2 wires are shrinking. And finally, apply the pre-stressing force to Zone 1 and 2. There could be 2 types of APS depending on the configuration of our target region. If our target region is relatively short, we can connect Zone 2 only to one side of Zone 1 as shown in the figure above. Or if our target region is relatively long, we can connect Zone 2 to both ends of Zone 1 as shown in below. To develop APS, we did some preliminary tests with single APS module in prismatic concrete beam just to see how our system works. We designed 3 inches by 3 inches and 2 feet long prismatic beam. For the SMA fuse, we used 8 wires of SMA wire with 2 mm diameters. And for the steel, we used 5.32 mm grade 270 low relaxation wire, which is typically used in concrete ties. For connection mechanism, we used 2 U-clamps with epoxy. Zone 1 was kept void for 2 reasons. One is for visual inspection during the activation of SMA fuse, and 2 is for easy access during the activation. In this preliminary testing, we used small diameter SMA wires and voids in Zone 1 and connection mechanism with U-clamps, but all of these details can be improved in the full-scale ties. Here is the close-up image of the APS module. The pre-stressing force in APS module is determined by the length and the area ratio between the SMA fuse in Zone 1 and unbonded steel in Zone 2. The length ratio between the steel over SMA was 1.6, and the area ratio between the SMA over steel was 1.13. And resulting pre-stressing force of the APS module was 2.68 kip, calculated using Hooke's law and the force equilibrium. Zone 2 is covered with nylon sleeves to debond from the concrete. I conducted activation tests with the beam. I applied heat through the void using torch flames for 10 seconds to activate the SMA fuse. Speckle patterns was applied to the specimen for DIC. The camera was set up in front of the specimen and captured images during and after the activation. Here are the results of preliminary testing. The figure in the middle shows the strain distribution of the specimen after the activation test from DIC. And the bottom figure shows the strain distribution from the finite element modeling. I adjusted the manufacturing errors in the test specimen that the steel wires at the right side of the U-clamps are bent up towards the top. After the adjustment in finite element model, DIC and finite element modeling predictions showed good agreement to each other. After the preliminary test, we designed and tested a half-scale concrete cross-tie specimen. APS was located to pre-stress the top of the center region and the bottom of the rail seat region. To provide compressive reinforcement at the rail seat section, 2 non-pre-stressed steel wires are placed at the top. And for the center region, the black dashed line representing the zone 3 of the bottom APS module act as a compressive reinforcement. In the specimen, we adopt all the design details of APS module from the preliminary test. This is a cross-section view of the test specimen in rail seat and center section. At the rail seat section, 3 APS modules were placed with 1-inch eccentricity. The designed APS can pre-stress 102% of the stress at the bottom of ARIMA-based reference tie. At the center section, 2 APS modules were placed with 0.6-inch eccentricity. The designed APS can pre-stress 66% of the stress at the top of the reference tie. We made void around the SMA fuse and the connection to visually observe the movement of the wires when it's activated. After deactivation, the void will be grouted. For that, we used a 3D printed mold with grooves so that it won't slip once it is grouted before service. For the activation test, similar test setup was used. I attached strain gauges at the critical sections and placed camera for DIC. The activation test was done one section at a time separately. The torch flame was used to heat the SMA fuse. Each section was heated twice for 30 seconds with an hour interval for cooling. During 2 hours of each side test, DIC camera and strain gauges recorded the strain of the section. First, left side of the rail seat was heated, and after 2 hours, right side of the rail seat was heated, and after 2 hours, center region was heated. This is the activation test results from the strain gauges. The graph shows the time history of the strain values measured from the strain gauges from rail seat left, rail seat right, and the center section from the top. The blue solid line shows the top strain of each section, and the red dotted line shows the bottom strain of each section. In the first 2 hours, rail seat left was heated. As you can see from the graph, the bottom stress instantaneously dropped to a negative value, which means it's compressive strain. And the top strain is increased to tensile strain. And nothing happens in the other sections. And after 2 hours, now the rail seat right section is heated. So right after the heating, the strain dropped instantaneously to negative values and is sustained in a certain level. And then at the second heat, there's another drop. This means that the SMA wire wasn't fully activated in its first heat. That's why we did the 2 cycles of heating. And after 1 hour of cooling, the strain value is sustained. And nothing happens in the center section. And after 2 hours, we deactivated the center section. And as you can see, this time there's drop of strain from the top because the APS module is located at the top of the section. And the red dotted line, which means the bottom strain, is slightly in tension side. From this time history strain measurements, it showed that each APS module does not affect each other and they work independently. And this is the axial strain distribution from DIC and the FEM model. As you can see, the strain distribution is showing good agreement with each other. And this proves that the proposed APS can actually apply pre-stress to target regions as designed. Loading test of the test specimen was also conducted after 30 days from the activation test. All voids were grouted the day before loading test. Rail seat positive and center negative tests were performed as per ARIMA MRE Chapter 30. Rail seat left was first tested, and the rail seat right and the center was tested lastly. For the center negative bending test, I was unable to test with the full length since the rail seat regions were already damaged, so the support pins were placed closely within the pristine region. This is a result of the loading test. All rail seat section from test 1 and 2 showed diagonal shear cracks and the crushing at the top. At center section in test 3, flexural cracks from the bottom and the crushing at the top was observed. The load displacement curve for 3 testing is shown on the right. Green dashed dot line represents the rail seat left section, which was grouted. Black solid line was, and the blue dotted line shows the rail seat right section, which was not grouted. Red dotted line shows the center negative testing result. Rail seat left shows greater cracking and ultimate loads than the rail seat right. This can be interpreted as the grout in rail seat left actually contributed to strengthen this section by resisting the failure around the voids. Cracking load of rail seat right was observed to be about 4 kip, which was closely matched with the nominal cracking load of the design specimen. Corrugated face at the intersection of the grout helped to avoid slippage by adding more friction at the interface. And here are some concluding remarks. The adaptive pre-stressing system was proposed using a small amount of SMA to make it economically feasible for commercial application. APS is comprised of unbonded SMA, unbonded and bonded conventional steel, and connection mechanism. SMA fuse activation tests using DIC and strain gauges showed APS can effectively pre-stress the target region as designed. Cracking loads at rail seat and the center sections were as designed. And I'd like to acknowledge the financial support from the Rail Safety Idea program under the project number 33. And we are also like to thank our project's external review panel for their invaluable help and advice. Thank you.